We're going to have a look at a few key equations related to work function and the photoelectric effect, as well as some key definitions. So just to start with, it's told you a metal has a work function of 2.28 electron volts. What is that work function, and how is it different from ionization energy? Well, if you think about an atom, its outer shell has electrons. There's electrons on the furthest inner shell, and then the furthest outer shell. The electron in the furthest inner shell, in order for that electron to escape the surface, it would need to absorb an ionization energy. So it's the minimum energy needed for an electron to escape from its ground state, meaning its lowest energy level. However, the work function is the amount of energy needed for an electron on the surface of the metal to escape itself. Now, where do these electrons get the energy from? Well, that's where a photon comes in, and the electron absorbs energy from that photon. Moving on from that now, it's asking you to show that the minimum frequency of radiation needed for a photon to ionize an atom is this much. So we want to relate minimum frequency to ionization energy, which is 5.15 electron volts. Because in order for this electron to be ionized, the energy that it gains is from the photon, and the photon needs to have a specific frequency in order to have that specific amount of energy, according to the equation E equals hf. If we rearrange this equation, F is equal to E divided by H. So the energy that the photon arrives with, which is the energy that is needed to ionize, 5.15 electron volts, that's what we use as our capital E. But you also have to convert that into joules. To go from electron volts to joules, we use the fact that 1 electron volt is 1.6 times 10 to the minus 19 joules. So you multiply by 1.6 times 10 to the minus 19. You divide all of that by Planck's constant, which is 6.63 times 10 to the minus 34, and that gives you a value of 1.24 times 10 to the 15 on your calculator, which is roughly what the answer's asking you to find. Moving on now, part C of this question, it tells you that radiation with this frequency is incident. Calculate the maximum possible kinetic energy of an electron that is emitted when a photon of this radiation is incident on the surface. So what that means is, well, do you remember we talked about how there's a difference in energy between ionization and the work function? If instead this electron absorbed this specific amount of energy that we found is needed for ionization, how much extra energy would it have after being emitted from the atom? That's what it's asking for. That's the possible kinetic energy. So we take that energy that it would absorb, the ionization energy, and we use the fact that the maximum kinetic energy is the energy that it would absorb, which is 5.15 times 1.6 times 10 to the minus 19, take away the energy needed for it to actually escape the surface, the electron on the surface that is, and that's what we call the work function. So you have to convert this into joules before using calculation. You might have seen this equation as EK max equals HF minus work function. If that's easier for you to use, go ahead and use that. HF would be the ionization energy because that's the amount of energy that's being absorbed if the frequency is the same as the frequency that we calculated here. The work function, I would just convert that into joules, so times 1.6 times 10 to the minus 19. Putting all of that into your calculator, you'll get a value of 4.59 times 10 to the minus 19 joules. Perfect. Moving on to this part now, it says calculate the speed of an electron that has the same de Broglie wavelength as the EM radiation in part B. So first of all, what is de Broglie wavelength? Well, it's Planck's constant divided by momentum, which is mass times velocity. So to find the speed of the electron, that means we're going to rearrange for speed, h over m lambda. We know h is Planck's constant, it's given to you in an exam. We know the mass of an electron. We need the wavelength of the electron, and we use the fact that it has the same de Broglie wavelength as part B. So how do we find the wavelength in part B? Well, we know that a photon travels at the speed of light, and we know the frequency of that photon. You can use the fact that wavelength is, well, rearranging speed equals frequency times wavelength, that is. You get wavelength is speed over frequency. So it's the speed of a photon, which always travels at the speed of light, divided by the frequency of that photon, which is this value here. 1.24 times 10 to the power of 15. Now, on a calculator, that will get you a value of 2.42 times 10 to the minus 7 meters, Once you've got that wavelength, you can put it into this equation along with all other variables. So the speed is Planck's constant divided by the mass of the electron, which, like I mentioned, is given in your equation sheet, multiplied by that wavelength that we just found, 2.42 times 10 to the minus 7. Now all of that actually just equals to 3010 meters per second, and that's your final answer here. Lastly is this worded question, which it makes sense, and let's go through why. So it says that this much frequency is incident on the surface and electrons of this much kinetic energy are emitted. Why the electrons have a range of kinetic energies up to a maximum value? Well, that's because of what we mentioned before, the fact that electrons in the deepest inner shell would need more energy to escape the surface than an electron on the furthest outer shell. Comparing it to an electron here, this would need more energy than this one because it has to excite first to the high energy level and then escape. Does that make sense? So you want to mention something along those lines, that electrons deeper in the energy level use up energy for excitation. And because some of the energy is used up for excitation, less energy is available as kinetic energy once it escapes, if the same amount of energy was absorbed from a photon. Less energy available for sorry, my mind went blank. Kinetic energy. Along with that, you can mention the fact that kinetic energy, the equation for it is hf minus work function. The work function of a material is constant, but the frequency of the photon might be different if it's a different photon. That would then affect the energy of the photon. If the energy of the photon was smaller, and you're doing a smaller number take away a work function, you're going to get smaller kinetic energy. If the energy of the photon was larger, you do a larger number take away work function, which will give larger kinetic energy. Hopefully that will make sense. Writing all of that up will definitely get you the 3 marks here. Quite a long question, but hopefully that all made sense. If you have any questions with it, just let me know. If you'd like me to go through some of the theory as well, you can let me know as well.